So then I just put x on one side and then the constant on one side. So I just solve for it to make x equal find the value of x that equals it makes the two equations equal to each other.
Oh, you just do by observation. Just by observation, right?
Yeah.
Okay. One way is by observation. Maybe sometimes we won't be able to do by observation. What is a systematic way to do this?
Usually you set it equal to 0.
Okay. Yeah. You see, this is the quadratic equations.
Yeah, I would bring the 1 onto the other side and make it equal to 0. I thought this is also one way of just making it equal to 1.
So you were saying, okay, that's 2x squared plus absolute value of x, then minus 1 equals to 0, right? You see here? So now from here, can we do something else? Just like you observed. What does it mean absolute value of x? You get two solutions, right? One is when x is positive. If x is positive, just add x. Minus 1 equals to 0. Get this. Then we have another one, right? 2x squared. But x is a negative. Absolute value of x will be negative x, isn't it? We get those two equations. Does that make sense?
Yeah.
Okay, so from here, what we can do? Can we solve those two quadratic equations?
If you factor them.
Right, how do we factor them? The absolute value of an expression always give us two, right? One with positive, one with negative. Can we factor the first one?
One of them is 2x plus 1 times x minus 1.
Right? Okay, that gives us two solutions.
Then it's
How do we factor the second one?
2x minus 1, x plus
Right.
1.
Exactly. We just switch that factors. Solve those two equations. How many answers we get? How many solutions we have? Have 4 solutions, right?
Yeah.
So can you tell me which 4?
Negative 1.
Negative 1.
1.
Positive 1.
Negative 1/2.
Negative half.
And 1/2.
And the positive half. All right. So this is a systematic way, right? So now you have these 4. You have these 4 points. So go back to the function, right? So x equals to 1 minus 2x squared. Y equals to 1 minus 2x squared. Y equals to absolute value of x. So we did this a systematic way. We have x equals negative 1, negative half, half, and 1. Now what do we do? You draw the graph. You can draw the graph, right? So 1 minus 2x squared. Let me see if I can draw here. Oh, it's supposed to be symmetric. So 1 minus 2x squared. Actually, I should let you draw it. Do you like to draw it? So now we have 4 solutions. Let me write these 4 solutions again. X equals to -1, -half, half, and +1. We have 4 solutions, right?
Yes.
Right. So can you tell us? So now, what should we do? What's the graph of y equals to absolute value of x?
Just a V shape, like it.
Yeah, it's a V shape, right?
The V shape center at y equals 0, I think. X equals 0, x equals 0.
Yeah, right, the vertex is 0, 0.
Yeah.
All right. So we have 4. So if we draw systematic way, we have 4 solutions. We have 4 solutions of x. But if we draw the graph, let me draw the graph.
It only intersects at 2 points when you draw the graph.
Exactly. That's the point. Exactly. We will have like this. There's only 2 points intersect here, -half and a half, because it's enclosed by this. Now you can see, okay, I can ignore the other 2 solutions. Right? I can ignore this. I can ignore this. Then the rest of it, I have a comment on this one. Oh, okay, now I see it. So this is your integration sign, right?
Oh, yeah.
I see. I was like, right, okay, so this is your integration sign. You say, okay, my integration sign, my lower limit is -half, my upper limit is half. So the integrand is the upper one, subtract the lower one. The upper one is the parabola 1 minus x squared, and it's the lower one, absolute value of x, dx. Now, how do we? So you should carry the sign, right? With you, if you have dx, this is the point. See, if it's only dx, that doesn't make sense. Dx has to go with the integration sign.
Okay.
Okay. Now you said, okay, 1 minus x squared minus absolute value of x. How would you evaluate? How do we evaluate absolute value of x? The integration sign. Let's just think about this. Absolute value of x dx. I think someone showed before. I hope the rest of you are paying attention. This is a very important concept, and it will be surely on your final exam. Let's make an easier one. Let's say go from -1 to 1. All right. This is just an example. Right. If you think about it, ignore this parabola, right? Go from, how do we find the area goes from -1 to 1 for absolute value function of x. Because you skipped. You skipped the process, right? Sandy,
Yeah.
can you answer this question? Can you do this?
The absolute value of x to -1.
Remember what have we done before? We split it into 2 integrals, right? think about from -1 to 0, then from 0 to 1, because there's no formula for anti-differentiate absolute value of x.
X. Yeah.
Okay, so what do? We think about splitting into 2. Think about from -1 to 0. From -1 to 0, x value is negative. X itself is negative. The absolute value of it becomes
Positive.
right. So we have to put a negative x because this x is negative. Negative and negative become positive. So we split it into this one and a plus. Then from 0 up to 1. From 0 up to 1, x value is positive. We just have x dx. Now we can integrate. Now we integrate, right? We won't be able to directly integrate absolute value of function. We split into half, right? We split into, right, positive side, negative side. Now we can integrate. So your calculation, do you see it missing this part? Does it make sense for you?
Mostly, yeah.
Yeah, because we don't know how to evaluate, how to integrate this. There's no direct method to integrate this. We have to think about splitting into this. All right, thank you, Stanley. If you can, I don't know. All right, let's see. Thank you, Stanley. Anyone else did 3? So that means someone else can show 3.
You got me, Carlos.
Stanley did not complete it right, and if anyone wants to show 3, you still can show 3. Anybody? All right, so I almost give all the answers, right? The rest is just evaluation of the two. Actually, the two integrals are the same. So you just need to double one of them. You just need to calculate one of them and double it. Okay, let's see. Who's next? Oh, Karen said Karen can show 3. Okay, go ahead, Karen.
Sorry, I have asked for 3 before. I was in the chat.
Oh, okay. Who's this? Sorry.
Carlos?
Oh, Carlos. Okay, go ahead, Carlos. Great.
Okay, so we have to. Do you want me to read the question as well?
Yeah, start from the very
Okay,
beginning.
so we have to find the. Okay, we have to find the area of the region bounded by the given curves. So I didn't sketch, so it wasn't asking for a sketch. So we have y equals 1 minus 2x to the second power equals to and y equals the absolute value of x. So I did case 1 and case 2, which x is positive and x is equal negative. So we have to equal them to 0, and then we have to factor it. So I got 4 points. So x equals 1.5, or x equals -1, and I have x equals -1/2, or x equals 1. But we only had to use the values that are true. So we were to so we only use -1.5 and 1.5, positive 1.5.
How
Okay,
do you know that? How do you know?
how?
How do you know, right? One and 1.
What do you mean? Sorry, I couldn't hear you.
I'm sorry. So you see here we have. Let me use my pen. The question is this: x, you have 4 values, right?
Mm-hmm.
How do you know this interval, -1/2 to 1/2?
Oh, it's supposed to be here, true. sorry, it's not there. So if you plug in values of -1.5 or -1,
Oh, I
so
see.
yeah, so plug in by -1.5, we get x to the absolute value of 1.5, so they equal to each other. So, I didn't think it was necessary, but I just put out true. Sorry, it's not there. I put out the other side.
Right. I see. So I hope the rest of you are listening. Carlos is saying he gets 4 values. He just plug back into the the very first equation. The very first equation he did not write down. The very first equation Stanley has it. It's 1 minus 2x squared equals to absolute value of x. Right? Set those two equal to each other. Only -1/2 and 1/2 satisfy this equation. -1 and 1 would not satisfy the equation of those 1 minus 2x squared equals to absolute value of x.
Okay, yeah. So then we
Good.
and then you say something about last time about both symmetric over the y-axis, and so we only use we integrate from we take 2 to the left side, and we integrate from 0 to 1.5, positive 1.5, and then we integrate the actual the beginner equation here, and we set them up as 1 minus 2x minus x, and then we've had to find the derivative of the equation, and then we get 2 parentheses. Okay, after we found that this is the derivative, okay, and then we have to evaluate from 0 to 1.5, and then after that we just plug in 1.5. I left out 0 because we'll get a 0 value either way, and then after plugging in 1.5 for x, we substitute all of x for 1.5, and then we get the value 1.5 minus 1.5. I mean, sorry, this was supposed to be at 12. I don't know why. Minus 1 and 8. We have 2 parentheses 724, and that's how we get our area.
Okay, just let's make this clear. So from this, because you didn't show how did you, so the area of the enclosed equals to 2 double of this 0 to half. And also your one is 1 minus 2x squared minus x. So what's, something is here, some assumptions here.
Do we have to find the antiderivative?
So we have to find the area from -1/2 to 1/2 of those, the area, right, the area of the region enclosed by those two functions. As I draw the picture before, right, we need to find the area. We need to find this area. Right?
Yeah.
Okay. So I just need you to explain why you made a 2, the integral from 0 to 1/2. Then the inside the integrand.
Okay, somebody did the same question last time, and I just got it from the same steps she almost made. And I also saw it from the 2.2 that the review, and they also were left in out the 2. Is it because we take in 0 to 1.5, and you say both are symmetric over the y-axis?
Okay, great. That's right. So if we draw the graph, we see it's the symmetric. The graph, the area of this region are symmetric with y-axis. Okay, great. That's a good point. And then why the integrand is like this? Why this is the integrand?
Oh, we take the
That's something to do with your lower limit and upper limit.
yeah, lower we take minus a to b.
No, you're assuming x is positive here, right? Because from 0 to half, x is positive. That's why you do not have minus negative x. You have minus x.
Can you repeat that again? What is it called?
Okay, my question was this. Why your integrand is 1 minus 2x squared minus x? This x has something to do with your lower limit and upper limit.
Mm-hmm.
Your interval you're working with is 0 to half interval. So that means you're assuming x to be positive. Right?
Mm-hmm.
That's
Yeah.
why you have your upper function subtract your lower function. So you have this part of the function subtract the lower part of the function. Because of this interval from 0 to half, the x value is positive. So you have minus x, not minus negative x. Or someone could use the other side. Someone could set up this integral from negative half to 0.
Oh, okay. I see it. Huh?
Yeah, then the x value is negative x. Then you will subtract the minus negative x.
Yeah, that's why I let a parenthesis. And we know that we have a
You
one.
did it right. You did it right. You did it right. It's just something behind. There's some reasons behind the action. Okay. Anyway. All right. Good job. Thank you.
Okay,
But
thank
anybody
you.
have any question? This is a good final question. This kind of question is a good final question because it involves many stuff to be understood. Okay. Carlos, you have any question?
No, that was it's good, right?
Yeah, that's good.
Okay, thank you.
Right. Okay, 3. Oh, I should have left for Karen to explain some points. Okay, anyway, Karen, do you want to show 3 also?
Oh, I got the same answer, so it's fine.
Oh, all right. I don't really know what are some questions left. Let me just copy out this. Let's go from the very start. So we have 4, we have 3, we had 1, 1, 3, 4. Alexandra wants to try 2. Alexandra, go ahead. 2. How many questions are left? 1, 2, 3, 4. I only left 4 questions. Oh, I see. Don't worry about it. I'll give you time to present. All right, Alexandra, I see your work. You can explain.
Okay. Good morning. I'm sorry.
Yeah, go ahead. I'm sorry.
Okay. So I'm doing number 2, and we're given 4 functions. And so first, I wanted to graph it to see, and I had left. I had graphed each function, so whatever the color is boxed in, so y equals 1 over x is in orange, x squared is in red, and I already knew that y equals 0 was the x-axis, so I left it that way, and x equals e is between 2 and 3. So I'm not even sure if I got this correct, but if I'm wrong, that's okay. I had split it into 2 areas, and I found that 1 over x being equal to x squared, that would intersect at x equals 1. So I knew that this was an area from 0 to 1 and an area from 1 to e. So I knew that from here, I knew that the interval from 0 to e was 0 to 1 plus 1 to e. So I found the interval first from 0 to 1. The upper limit I knew was x squared, and the lower was 0. And I found the antiderivative, and I plugged in the solution for 1, and I already knew that was 0. And the value for the first area would have been 1 over 3. And then I found the second area, which was from 1 to E. And then I knew that the upper limit was this time 1 over x.
That's not the upper limit. Where is your lower limit, upper limit?
Upper limit would be for the second area.
No, right. We call those guys lower limit. The integration, the interval where integrate. On the bottom, on the full note, we call lower limit.
Yeah. So
On the
the
top, we call upper limit.
yeah. I'm sorry, I worded it differently.
Those are lower limit, upper limits. And this is the upper function.
Yeah.
Yeah,
right.
lower function. Okay, all right, go ahead.
Sorry, I worded it differently. So the upper function would be 1 over x, and the lower function would just be 0. And the upper limit would be e, and the lower limit would be 1. So then I solved it. I found the antiderivative, and I plugged in both for e and 1, since I knew antiderivative of 1 over x is just ln, absolute value of x. I solved for each value, and I had gotten 1 minus 0, which is 1. And since these are two separate areas, I added them. So 1/3 plus 1 would be my final answer, 4 over 3.
Great. Okay, the answer itself is great. Let me just ask you one more question. So 1 over x, when we anti-differentiate, we get ln of absolute value of x. Can you explain to me why we need to put absolute value here?
I'm actually not sure. I just knew I memorized the antiderivative of 1 over x.
I see. Well, can you graph ln x? What's the graph of ln x? Let me graph for you. Something like this. Oops. Something like this. Oops. So think about this
Yeah.
curve. Okay. So what is the domain of the function ln?
Oh, it's 0.
Domain, O-M-A-I-N. So let's say we have a function f of x. Oops, so small. Think about this function, f of x equals to ln x. Okay? No absolute value sign. So what is the domain of this function? The graph looks like this. You see, on the right-hand side of the y-axis, think about the x values. What are some x values work for this function?
All positive x values.
All positive x values.
Yeah.
Which means
That the domain would be from 0 to positive infinity.
no zero, right? X close 0 has to be all greater than 0, all positive. That's why we're forcing this x to be positive here. Once we anti-differentiate, we force the x value to be positive.
Okay.
The domain of ln cannot be 0, cannot be negative. That's why we need this absolute value. Great. Okay.
Okay.
All right. Thank you. This so this is Alejandra. Okay, it's 8 o'clock. Since we still have time, let me see. So I only left. Okay, let's talk about the volume. And I want to thank you first. I want to thank all of you, all right, prepared to show the work, which is great. And I will surely give you enough time for you to prepare, to present, all right? This is a great spirit here. Thank you. So now let's talk about the volume, okay? The concept is like this. Okay, now think about, am I sharing? No, I need to share my screen with you. So think about, so anybody has any questions? Let me make sure I give them credits for presenting. Sometimes if you may get half credits, all right, for presenting. If you're not able to fully answer my questions. Let's see, so Julia, when can I present 21? You can present 21 now, Julia, if you're ready. Anybody else like to present? Let me just go through this. Yes, I'm trying to. Right now, I think I have 30 questions. I have compiled 30 questions for the review sheet. Because we still have time, I'm trying to, at least come up with 40 questions. So everybody would have enough chance to present.
Hi, can you hear me?
Yeah, remind us of the question. This is in which homework?
So you just added it
In
today.
which
It was.
homework?
I'm sorry, what was that?
In which section? 7.1?
I think so, yeah.
Okay, go ahead.
Yeah, so the question said to sketch the two areas bounded by the four functions of x equals 0, x equals pi over 2, y equals cosine x, and y equals sine x. So over here is x equals 0, x equals pi over 2. This one is y equals cosine x, and this one over here is y equals sine 2x. And so I wasn't sure. I think that these two are the two areas bounded. I just wasn't sure if this left region was a part of it.
What do you mean? So you have four bounds, right?
Yeah.
You have x equals 0, x equals pi over 2. So x goes from 0 to pi over 2. Then one function is y equals cosine x, the other one y equals sine x, sine 2x.
Yeah.
Which part you're not sure?
I just wasn't sure because the question said that there was only two areas that were bounded, but I don't know, I see three.
X equals 0. Which three are seeing? I only see two.
I don't know, because I see this far one on the left over here that I'm shading in with blue, and then the other two that I already sketched in.
This one you see here, are you talking, are you talking about this one?
The one on, yeah.
Is this one bounded by y equals cosine x and y equals sine 2x?
Yeah.
Really? It's not part of cosine x, right? It's part of sine 2x.
Oh, okay.
It's not
Yeah,
part of. It's not
yeah, I just had that one question about this problem. Okay, so then the two that I already shaded in are the areas bounded.
Oh, let's see. Okay, Noella says the graph is not correct. Let's try to see. So cosine x goes from 0 to pi over 2. Oh, no, this is cosine, right?
Professor, could I mention the only mistake that she made?
Yeah. Go ahead.
So the only mistake that she made was shading it in that triangle that's connected to the y axis. That's the only mistake that I can vividly see. That's the only place where she incorrectly shaded. But where you have the red ink and the other part that she shaded are incorrect. And we have to find the area of those and then add them together.
I see. Right. So do you hear that? This is
So then it's only the left and right parts that are bounded?
well, let's check your graph. So your graph is, so this is the y-axis. So let me use the red color. So x equals 0, that's your y-axis here.
Mhm.
And this is a pi over 2. So what is the graph of cosine x? Which one is your graph of cosine x?
This top one over here. That one.
Let me erase this. Which one? Can you mark again? Sorry.
This one. I don't know if I can make it wider.
Oh, this one is your cosine x?
Yeah.
No. Cosine x, what's cosine 0?
1.
Yeah. So your graph should start from here. Let me use a different color.
Yeah, it starts. Oh, wait.
Right? Your graph should, so y equals to cosine x should start from here, right?
Yeah.
Oh, I think you're right. You just did this one. You should switch this one. This, let me make a red color. This should be your y equals cosine x graph. See that? What's
Huh.
cosine pi over 2?
Pi over 2?
Cosine pi over 2.
90?
Cosine pi over 2 is a value, it's a number.
Yeah, no. 0?
0. Oh, Julia, my goodness, you have to know this, right? What's cosine pi?
It's -1, right?
Right, cosine pi -1. What's cosine 3 pi over 2?
0.
That's right. Okay, so your graph is wrong. Do you see that?
Yeah. Okay. Yeah, I see
Your
it.
graph is wrong. Okay, so let's see. I think someone else wanted to show it. Okay, anybody else wanted to show 21? Also, I left the 20, right? Right, I said try 20 and 21. So somebody else can show 20 as well. So we have 20, 21. Oh, Amir, which one you want to show? 21? Maybe somebody else can show 20. It's on 7.1. So I left it 2. 20 and 21. All right, let's right. Okay, Amir wants to show 21. Let's go ahead. Try 21.
Okay, Professor. So I'm just gonna restate the question just so we don't get confused again. So for 21, we're given y is equal to cosine x, and we're also given y is equal to sine of 2x. And we're also given that x is equal to 0 and x is equal to pi over 2. So if we were to graph this, 1 second, sorry. Oh, sorry. Anyways, if we were to graph this, we would see here that sorry. Right, so we have your y equals cosine of x, and y equals sine of 2x. So our graph would look something like this. So we'd have here 1 here. We also have here, let's say pi over 2 is over here. Then we could also have here a negative pi over 2. And then, alright, so for cosine of x, we have something like this right over here. Turn up. And then let me see. Yeah. And then also we have your y equals sine of 2x. So then we would have here it would start at 0. And then we see here that at some point it would intersect at pi over 6. So it goes something like this, right? And then go back down. So this right here, these two are shaded regions we're trying to find. Second.
How do we know they intersect at pi over 6?
Well, if we set them equal to each other. So do you want me to do that, Professor?
Yeah, let's do that.
Okay. So we have your cosine of x equals sine of 2x. And then what we would do from here is one second. Okay, so we know that cosine of x, sine of 2x, that would be what do you call it? 2 sine of x cosine of x, I believe, something like that.
Okay, double angle formula.
Yeah. Alright, so then we would divide by cosine of x on both sides. You get 2 sine of x equals 1. So sine of x, that would equal half, and we know that sine of pi over 6 is half. Alright, and then all we have to do from here is so just to be clear, let me just label these graphs quick. So our So this one right over here is y equals cosine of x. And this one right over here is y equals sine of 2x. So we can clearly see that from 0 to, we have our two bounds from 0 to pi over 6, and also from pi over 6 to pi over 2. So our area is equal to this. So for the first one, we would have your pi over 6 and 0. And then you can see here that our upper is cosine of x, so we would do cosine of x minus sine of 2x. And then we also are we can see for our second one that we have here sine of 2x is greater, so sine of 2x minus cosine of x. So then we're basically adding these two.
Don't forget your dx. Otherwise, it doesn't make sense.
Oh yes. Okay. So then we have here pi over 2, pi over 6, sine of 2x minus cosine of x. And then a dx, as you said. Okay, and then all we do from here is we would solve them. So we would have here we just plug in the values. So for the first one, we just do, oh wait, first we have to find the antiderivative. So first what we would do is the antiderivative of the first one, that would be what do you call it? Sine of x plus half cosine of 2x. So and we're evaluating this at pi over 6 and 0. And then our second one over here would be negative half cosine of 2x minus sine of x. I mean minus sine of x, yeah. Alright. And we would evaluate this at pi over 2, pi over 6. And then when we solve each of these, we're going to just solve these and then add both of them. So when we actually solve them,
We evaluate this. We
yes,
evaluate.
we do f of the upper bound minus f of the lower. So when we solve this, here's a simplified version. If we were just plug in all the values, you would have your half plus 1/4. And then we would have your minus 0 minus half. And then plus half minus 1 plus 1/4. And then finally we would have here plus 1/2. And then all we have to do is simplify this, and our final answer would be 1/2.
Okay, let me ask you one question. Here, let me mark it.
Where, Professor?
Divided by cosine x.
Yes.
Because when we divide by something, we have to be very careful. That involves x. Cosine x could be 0. In this is 0 to pi over 2, right?
Yes.
We have to be very careful. The better way to do this is not to divide it by it, but to factor out. We move the two terms on one side. We factor out cosine x.
Oh, I see, Professor. Okay.
Then we get cosine x equals pi over 2, which is one of our bounds. Make sense?
Yes, Professor.
Okay, all right. Be careful with that. Be careful. Whenever we divide by a variable, we have to be very careful. The variable can be 0. We cannot divide 0 in math. Okay, great. Anybody has any questions? These kind of questions are pretty good for final exam. All right. Thank you. Take care, Mia. Henning wants to try 20.
Professor, can you make me the presenter?
Oh, I have not. I'm sorry. Oh, right here. And now you are. Whenever it's confusing, I really hope some of you ask questions, all right? So while Henry is getting ready, I'm going to talk a little bit about today. So after she finished presenting 20, hopefully I have a little time to talk about the volume. So now we're finding the area of the region. And the next step is we can rotate this region. We find the area of this region, then think about we're rotating this piece of region. We can rotate along x-axis, then we get a 3D object. Then we can talk about volume. We want to find the volume of the 3D object. Or we can rotate along y-axis, right? That forms a 3D object. Or we can rotate over any straight lines, right? Or horizontal, vertical lines or horizontal lines. It'll be a little more involved. But basically, we're rotating this region to get a 3D object. We try to get the volume of the 3D object. So that's our next section. And to find the volume, we have two different methods. And the second method is quite confusing for some people. I will introduce it, but it's not required. So I'm not going to test you on the second method. As long as you know that the first method is very intuitive. The second method, for some people, is not intuitive. I'm going to introduce and not require you to master it. Yeah, Hina, I see your work. Hina, your screen is up.
Okay. Well, I can't see it at the moment. So first they give you the
Remind me of the question.
they just give you the whatever I wrote right there. Y equal 1/4.
Okay, so what is given? So what do we have to do?
So I graphed it first. And then you see that there are two areas that are bounded. but we don't know it exactly, so I made it equal to the 3 minus x, which is the straight line. Find the
So we are trying to find the area bounded by those 4 equations.
yeah.
4 conditions. All right.
So to find the limits, I made it equal to the 2x squared equal 3 minus x, and I got 3 over 2 and 1. And then for the second one, I did 1/4 x squared equals to 3 minus x. I got negative 6 and 2. We won't use negative 6 because x needs to be greater than 0. And from there, I find the area, the upper limit and lower limit 2 to 1 because the graph is separated into 2 parts. And for the second one, you add 1 to 0. And then you plug in the upper function, lower function, and the same for the second part. And then you find the antiderivative of it. So 3 becomes 3x minus 1/2 x squared. And then it will become 1 over 12 x to the third. And the second one just turns to 7 over 4 x squared. And yeah, you plug in the upper limit minus the lower limit. And you do the same for the second part, and you get 3 over 2. I don't know how to explain it better. Does that make sense?
Yeah, let me ask you a couple questions. Again, presentation is not only reading what we have on paper, right? Presentation is basically explaining to people what's behind our writing. Let me ask you a couple questions. So first question is, how do we use the fourth condition, x greater than or equal to 0? So we have 3 equations and 1 inequality, right?
Yeah.
How do we use the first one?
It would just mean y is equal to 0. That's like the limit of it, because x needs to be a value that is greater than 0. So the least, what do you say, the y value, the limit of it would be 0 to infinity, kind of that.
Okay, so you're talking about,
Y,
so this x greater than or equal to 0 has something to do with our limits.
yeah.
Right. So this condition tells us everything happens in
The positive side,
positive side of x-axis.
the graph.
Right. So the graph goes this way. The first 2 graphs goes this way. So that's why the things happens in the first quadrant. All right, great. Now we have x value. Let's look at this line. We have x value equals to 3 over 2 and 1. X equals to negative 6, 2. How do we know to set up 2 limits like this, 2 integrations like this?
Because in the graph, it's like they intersect at 2 different parts. Is that 2 different parts? Can I say it like that or no?
Yeah, yes.
Like the first region and then the second region that's like kind of separated. So we can just like do it all together.
Right, right. That's the reason we set up into 2 integrals. So how is each one being set it up? Let's see the first one, from 1 to 2.
That's where they intersect with the lines. And I get the value from making them equal to each other too.
Okay, so you're cutting along x-axis, right? So from 1 to 2, you're thinking to cut it like this way. So then you said, okay, my left-hand side, my right-hand side is 3 minus x. Then does that make sense to you? This integration from 1 to 2. All right, let's check this from 0 to. It's from 0 to 2 or 0 to 1? 0 to 1, right? 0 to 1.
Yeah, 0 to 1.
0 to 1. So can you explain to us 0 to 1? I'm just telling you the first integration has to be split into 2. But we'll talk about this later. Maybe someone else can show. So the rest of you, I hope you are listening and try to see where the mistake occurs. All right, let's try the second one. So from 0 to 1, can you explain to us the integration of this part of the integration from 0 to 1? Basically this one.
Oh, wait, do I need to use the 3 minus x?
So you're talking about, don't talk about the first one yet. I'm going to talk about the first one. The first one is kind of complicated. So let's deal with this one from 0 to 1 first. I'll tell you what's wrong with this, with 1 to 2, okay?
Okay.
So let's now focus on from 0 to 1.
It's just like where they end and begin, like that's the graph. Like the first graph you see is 1/4 x squared, and the second one is the 2x squared one. So you use like that's the upper limit, upper function and lower function. The 2x squared minus 1/4 x squared.
Okay. So it's a good try overall. But let's see the first one from 0 to 1, right? Let's look at the picture. Let me take that color. From 0 to 1. Here, right?
Yeah.
I'm just assuming your graph is right. So that's this part. This is 0. Let's see. So the 1, you get a quarter. 1, you get 2. Right, okay. No, it doesn't work. From 0 to 1, 1 to 2, it wouldn't work for this integration. The picture is right. You see why? You see from 0 to 1, you have a region in 2 parts. In this one, and the second for the second function has a little bit also.
I can't really see what you're drawing.
Yeah. Just thinking about your picture. So this is x squared. This is a quarter x squared. So quarter x squared, you have these two intersections. You have -6 and 2. Then you have 3/2, 1. So assume your picture is right. If you split it into those two integrations, that wouldn't work. You see from 0 to 1. From 0 to 1. Oh, okay. Now I think, let me erase this. This one is not, you're not trying to find area of this. You're trying to find area of this only. Oops. You're trying to find the area of this. This is the only thing being bounded by these 4 things. See it?
Yeah.
Yeah. Not the other one you shaded. No. Not this one. Not the blue.
Wait, so I don't find from 1 to 0?
Not this part. No. I was just misled by the picture. Shaded. Don't shade this green part. Make sense? You see my red color?
Oh, okay.
The red color is the only area you need to find. Now your limits are right. Now your limits is setting from 0 to 1. From 0 to 1. Then your upper function is x squared. The 2x is 2x squared. The lower function is a quarter x squared. So this one is right.
Okay, and I see now.
Now
Sorry.
this one is right. I was confused by the shaded region. Then, so basically you're cutting from here. Use blue color. Trying to find the area of those 2 regions, not the 2 regions you shaded by. I cut it in blue color. Trying to find from 0 to 1, that's this one. Then from 1 to 2, from 1 to 2, upper function is a straight line. The lower function is quarter x squared. That's why you have this part. Okay, your picture. So now it makes sense. Now everything else follows. Does it make sense, Henning?
Yeah.
Okay.
I think it's so small. I guess I look confused.
Yeah.
The region.
Yeah. So this piece of region is being split into two because we have three. It's bounded by three functions. It's bounded by x squared, quarter x squared, and this straight line. So we have to split it in the middle, one in one. All right. So let's talk. Don't leave your paper here, Henning. Now we have this piece of region, right? We can rotate along x-axis. Imagine we rotate along x-axis, so we get something like this. Let me see, how do I draw this? I won't be able to draw exactly. Right. So when we rotate, we get a 3D object. And if we cut the level set, if we think about the level set circles. So the whole picture look like a cone, right? Look like a cone. And also we can rotate this along y-axis. Along y-axis, we will get this piece. Right? And again, the intersection for the level set are perfect circles. Then we can talk about find the volume of this object. All right, so let's start talking about our new material. Thank you, Henning. Oops, no, what did I do? Okay, volume. Right. This kind of stuff, volume, we know exactly how to find them. But we may have some special 3 object. The idea is the same, right? We do approximation with n pieces as a rectangular prism, so 3D rectangular object. Then we have the area multiplied by the depth, right? We have a 3D, we have volume for 3D object. We just add them up. Then we cut in these pieces into infinite many. So we get volume, get exact volume of the 3D object. Idea is still the same from Riemann sum. So let's see this piece. Let's see the volume of this. Volume of this, we can think as we have this piece of region. We have this piece of region. Now we can rotate along x-axis. So when we rotate, we get this 3D object. Right? What's the if we cut vertically? Think about the level set of vertically. We have those perfect circles. We have those perfect circles. So how do we find those volume? We just add up all those circles, right? Cutting from 0 to 1, we're cutting into infinite many pieces. And we just find the area of this each circle. Well, let's think about what's the area of this each circle. Okay? We can set up integration from 0 up to 1, cutting along x-axis. Okay? Cutting along x-axis. Then the integrand are those circles, area of those circles. So what's the area of those circles? Pi r squared, right? So pi we know. How do we find r squared? What's r squared? What's r? So all we have to do is to find r. So pi r squared. We need to figure out r. So r equals to, what's r? Well, let's see. Let's check the outside one. The r is this guy. R is this guy. What's this guy? Let's compare to the region. What's this guy? It's a function value, right? That's function value for this case. It's f of, well, y here, right? So it's y squared in this case. Y equals to y. We will have pi. Well, pi is constant, so we can leave outside. It's a function being squared for this case. Or we can rotate. This is rotating this piece along x-axis. Now let's rotate along y-axis. When we rotate along y-axis, what do we get? This is supposed to be exactly symmetric with this, right? Symmetric with this piece. This kind of. Oops. I have this piece. Just think about this piece exactly same as this piece. Just a reflection over y-axis. I have this 3D object. The 3D object, if I cut horizontally, if I think about the level sets horizontally, I still get circles. Right? I still get circles. You know, anywhere I cut, the level set are circles. So I still have this. So now, but I'm cutting along y-axis now, right? Think about I'm cutting along y-axis now. And then each level set is a perfect circle. So what I'm going to do, I'm going to set up an integral for y from 0 to this point. Well, what's this point? The x value, y value, right? X equals to 1, y also equals to 1. We're talking about this square root of x. So this point is 1, 1 point. So this is a 1, 1 point. So the y value also, so if I cut it along y-axis, so this is a y. And the y also goes from 0 to 1. And now what's my r? My r is not y anymore. What's my r? We see r is this one. So let me just delete this. We say my r is this. Okay? This guy's become my r. Because I'm trying to find the volume of rotated this region. And this here won't be included. So this empty is not part of the volume. The volume is this. So what is r? R is from this function square root of x up to 1, right? Up to 1. So my r, let me write here. So it's all about figure out the r. So r equals to 1 minus, 1 is fixed, right? So everything from this function up to 1. So 1 minus square root of x, well, 1 minus y. 1 minus, no, not 1 minus y squared. I'll tell you why is 1 minus y squared. Because we want to write this x in terms of y, right? We want to write this. So y equals the square root of x. That means x equals to y squared. Because now x is dependent on y, right? You see, because we're fixing y direction. We're fixing y direction as a constant. Now the x value on this curve, x value on this depends on y. So we want to write x in terms of y. Y equals the square root of x. Same, we can write as we square both sides. Write x equals y squared. So this r is 1 minus y squared. Then we put it in the integrand. So we would get a pi times parentheses 1 minus y squared squared because r squared. Okay, any questions? Let's see some examples. So again, the trick is to figure out the r. Okay, We are finding the area of the circle. Then we add up all the areas of the circle. And so the job is to find the radius of the circle. Where did you get the 1 from? Okay, let's see. You see this picture? This region is from 0 to 1 on x-axis. And this function is the square root of x. So that means this point here is still 1. It's 1 comma 1. This point. So this constant bounds are important. This point here, right? This one, so we need to figure out the length of this. Let me change my color. We need to figure out, you see, this is our radius. Oops. See these ones here, these ones are radius, right? At this point, this is the radius of this circle. Should I draw a circle? Okay, we are adding up all those circles, the area of those circles, right? At this point, the circle looks like this. What's the radius? The radius is this much. But how do you figure out this radius? This radius is up to 1, right? This side is up to 1. But what about this side? This side depends on y. Depends on y. Right? So the radius equals to 1 minus this part. Does that make sense? 1 minus this part. Okay, great. Let's see some examples. Find the volume of the solid obtained by rotating the region bounded by y equals to x cubed, y equals to 8, x equals 0, and the y-axis. Okay, so this region is bounded by 4 things. Let's draw the graph. We have y equals x cubed. Y equals x cubed is this graph, right? So this one is y equals to x cubed. Then what else? Y equals to 8. Y equals to 8. So this one. Y equals to 8. X equals 0. X equals 0 is the y-axis, right? And x equals 0. X equals 0 is y-axis and what? Or 3. So we have a y equals to x cubed, y equals to 8, x equals 0, about the y-axis. Okay, let's find the region. So the region is bounded by these 3 things. X equals 0, y equals x cubed, and the y equals 8. So we have this region bounded by 3 things. Now we rotate this along, we rotate along y-axis, right? But later on we can rotate by x-axis. So we rotate by y-axis. Then we get this 3D object. Let's find the volume of this. So we see we would cut horizontally, right? As horizontally we see each intersection or each level set the perfect circle. Perfect circle. So we just set up integration from 0 to a, cutting along y-axis. Cutting along y-axis. So from 0 to a, cutting along y-axis. Then we need to find the area of each circle. We need to find the area of each circle. How do we find the area of each circle? Pi r squared. So pi is a constant. We need to figure out r. What's r? Let's look at this point. Right? Let's look at this point. This is our r. This is our r. R depends on what? R depends on this curve. What is this curve? This curve is y equals to x cubed. Right? X equals y equals to x cubed. So y equals to x cubed. We want to, but x is our radius. So we need to be able to write x. What is our x? So basically, this pi r squared, the r is x. So r here equals to x. So how do we find x? So x, we want to rewrite this function, write as its inverse function. So x equals to cubic root of y. Because x depends on y, right? Because we're fixing y direction. Y direction are constant from 0 to 8. Now we want to write x as a function of y, in terms of y. So write it as a cubic root of y. This is our r, right? So x value is our r. The x value depends on y. So y equals x cubed, x equals to cubic root of y. Oh, you know what? I read this wrong. Cubic root of y. That's our r. So we do pi r squared, right? Pi r squared, r equals to cubic root of y, and then square, we get a y raised by 2/3. We just do the evaluation, right? Evaluation at 0 is nothing. Evaluation at a, so give us 96 pi over 5. So that's the volume of this object. At the same time, let's try to rotate this piece with x-axis. So when we rotate with x-axis, you get something like this. Oops. You get something like this. So imagine this is perfectly symmetric with this upper one, right? Then we're going to cut along x-axis. Cutting along x-axis, the intersection, we're cutting vertically. Level set are perfect circles. Then we add up the area of those perfect circles. So now again, we need to figure out our r. So we set up our integration. Well, let's set up from, we want to cut along x-axis, right? We want to cut along x-axis. We need out the lower limit and upper limit of x. Let's find this point. This point, when x equals to, when y equals to a, we know y equals to x cubed. So that means x equals to 2. So 2 comma 8. Right? So 0 to 2. So we're cutting x-axis from 0 to 2. 0 to 2. And we're cutting along x-axis. Dx. So this one we're cutting along y-axis. And we add the area of those circles, those horizontal circles. Here we're fixing x direction, 0 to 2. We're cutting along x-axis. Then we add up those area of the vertical circles. So again, we need to figure out. Well, let's leave pi outside. Pi is a constant, right? Not getting involved with the integration. All we have to do is find r squared and r. Inside, so we have pi r squared. What's r? So we need to figure out r. What's r here? Well, let's see r. R is just these guys, right? It's these guys. See, it's just these guys, r, right? At this point, r is this one. At this point, r is this one. Oops. R is this one. So on and so forth. Let me just delete. Let me just make one r. So we see r is bounded by the value a, right? Up to a. What about the lower part? The lower part depends on this function. Depends on this y equals x cubed function. So what do? We do a minus x cubed, right? So r equals to a minus x cubed. Let's put this r in, right? This r is a minus x cubed. Then we square. Then we anti-differentiate. Any questions? This piece is the same thing, right? We have this piece of region. First, we use a 2.1 material to find the region. Then we can rotate over x-axis. We will get this. Or we can rotate along y-axis. We will get this 3D object. Then we want to find the volume of this solid, right? We want to calculate this hollow region. We only want to find the volume of this solid. So example 5, find the volume of solid obtained by rotating the region in example 4. In this is another example. Basically this. We do that, we do the same thing, right? This one we have vertical circles. Vertical circles we cut along x-axis. So we see x value goes from 0 up to 1, right? Up to 1. So we set our integration lower limit 0, upper limit 1, the dx cutting along x-axis. All we need to have is find out the area of the circle, pi r squared. If pi outside, we need to figure out r. So what's r? R, here we see r depends on, so this one is, r depends on this, right? You see this one, I don't know if you can see it. Let me just make one r. See this r? Right? The r is this one, this line, subtract this one. Right? Basically, just this function, y equals x function, and then this one, y equals x squared, subtracting. So we have y minus y, x minus x squared. But remember, we want to find the area of the solid, not the hollow. So inside the hollow one is not calculated into the volume. So then, so in here, so what do we get? Oh, this is a rotate. So this is about the line y equals to 2. Right. So this is a tricky part. We're not rotating along x-axis or y-axis. This is rotating y equals to 2. So y. So this is the 1. Then y equals to 2. Let's see the picture. Where's the picture? Okay, it's time. I know it's time. I'm sorry. Okay, we're going to talk about this next time. But let me leave you some. Maybe you can practice. About x-axis. Right, let's just do about x-axis and y-axis. Okay, about y equals 1 we'll talk about next time because I was not able to cover it. Let's try. So I'll leave you something. Try 1 up to 8. Up to 8. All right. We need to find the volume of a region rotated by x-axis or y-axis. All right. Any questions? Okay. Thank you, guys. And I'll try to finish compiling these review questions. All right. And as long as I have all of them, I'll post it. Okay, thank you guys. Good job. Good job.